Right, hello linear algebra students. I will be out again on Wednesday, so I'm recording this lesson here about solution sets of linear systems. So let's go ahead and get into it. The first definition here, we're going to introduce some new vocabulary. We are talking about what it means for a system of linear equations to be homogeneous. It's pronounced homogeneous and not homogeneous. I've done a little bit of reading about that, and all of my professors in school would always say homogeneous. So it sounds wrong. Like in science class, we talk about homogeneous mixtures and stuff, but I believe it's pronounced homogeneous. If it can be written of the form uh, ax equals 0. Now let's make a little note here. This is a matrix vector equation. So we have a matrix A. So this is m by n, and the vector x is an n by 1. And this is going to give me the 0 vector, which is going to be m by 1. Okay, so the 0 vector is in R. It says Rn here. Did I mistype that in my notes? Let's read carefully. The matrix is m by n. The 0 vector is in Rn. I believe that is a mistake. Let's look. Where is x living? Yes, I believe this is a mistake right here. I believe that should be RM, but I will double check on that in a minute. Well, maybe I'll check on it right now. Just consulted the textbook. It is RM, so this is a typo. RM, which means that it's just got m elements. So this is the 0 vector in Rm. A system of this form always has a solution. The solution is if you let x equal the 0 vector. Then the 0 solution is usually called the trivial solution. So homogeneous systems always have a solution, and we call that solution the trivial solution. Sometimes they have more than just the trivial solution, but we call any other solution that's non-trivial, well, we call it a non-trivial solution. It's if and only if the equation has at least one free variable. So if we can find a free variable when we row reduce the matrix, then we know that the system has a non-trivial solution. So that is a solution that is not 0. Maybe I'll write that. So we'll say x that is not the 0 vector. If the equation ax equals 0, we're looking at the note here, note 1, has only one free variable, the solution set is a line through the origin. If there's two, the solution set's a plane, and so on, but we're running out of dimensional analogy there. The next definition, let's go ahead and read it. A non-trivial solution of a homogeneous equation can be expressed in parametric vector as a parametric vector form. So let's highlight that. Parametric vector equation, where you can write it in terms of S and T, where S and T are just real numbers, and U and V represent the free variables, or the vectors of free variables. So if we have two free variables, we can write our solution in that form. Okay, so let's keep on reading. This theorem, theorem 2, suppose the equation ax equal b is consistent for some b, which means that the columns of a b lives in the span of the columns of a, is consistent for some b, then let p be the solution. Then the solution set ax equal b is the set of all vectors of the form w equal p plus vh, where vh is any solution of the homogeneous equation. So this is a little bit convoluted what this theorem is saying here, but it's saying that you can rewrite all possible solutions in terms of one solution. So it all depends on finding that one solution, VH, where it's any solution of the homogeneous equation. So it's almost kind of like the root solution, I guess, and then you're adding that solution P to find the solution to some other system. Now, the reason that this theorem is valuable to us is because if we can solve the homogeneous system, then that means we can easily find a solution for a non-homogeneous system with some vector b, like that. So what we're trying to do, remember, for this course is we're trying to reduce the amount of work that we have to do when solving systems. And so what we're doing is we're finding a more basic system. What if it all equals 0 instead of equaling some vector b? And then what if this has a solution? What if the homogeneous system has a solution? Then will it be easier for us to find a solution of a non-homogeneous system? And the answer is yes. This theorem says what you can do is write all solutions in the form of the solution VH from the homogeneous system in terms of P, which is the solution of the homogeneous system, non-homogeneous system. So we're trying to reduce complexity here, but it feels like it's making it more complex. But we're adding these vocabulary terms and adding new types of equations here to help us kind of reduce work. So let's read this last note. It says, writing a solution set of a consistent system in parametric form. The first thing that you want to do is row reduce to find reduced row echelon form. Then express each basic variable in terms of the free variable in appearing in the equation. We've done that before. That's like the general solution. Maybe I'll write that there. So general solution. General solution. Write a typical solution X as a vector whose entries depend on the free variable, if any. So that's so that would be the general solution as a vector. Then 4 says decompose X into linear combinations of the free variables, so vectors with entries and using the free variables as parameters. Sure. Yeah, so we'll do that. I think I said U and V are the free variables, but here it's S and T are the free variables. I was kind of making a mistake there. But yeah, let's go on to the first example here. It says determine if the following homogeneous system has a non-trivial solution. Non-trivial, again, just a reminder, means non-zero. So it's not 0. Then describe the solution set. Okay, sure. Let's first write this as an augmented system. So 3, 5, -4, 0, -3, -2, 4, 0, and 6, 1, -8, and 0. Not everybody puts this vertical bar here, so you don't have to. I put it there just so that we are reminded that we're dealing with an augmented system. Let's start some row reduction. I'm going to eliminate the 3 and the 6 here, so this is going to be 0, 0. So the row 1 will remain unchanged. I'm not going to do anything with row 1, but I did add 1 of row 1 to row 2. So this is going to be a 3, and this is going to be a 0, and this will be a 0. I'm taking away to row 1 from row 3. So this is going to be a -9, and this will be a 0, and this will be a 0. And we'll continue down here. So let's divide row add 3, so maybe I'll write this one out. So we'll take row 3 and add 3 row 2 to it to replace row 3, and then we'll divide row 2 by 3. Okay, so that's going to be 3, 5, -4, 0, 0, 0. Now we got a row of zeros down there at the bottom. We eliminated that 9, and then we divided the second row by 3. And then we can eliminate the 5 above the pivot in row 1, or in row 2. So we'll get rid of that 5 by subtracting 5 of row 2. So it's going to be, whoops, I put a -3 there. We want a 3, 0, and a -4, 0, 0, 1, 0. Sure. All right, this is not RREF. We're close. We're almost to RREF. So reduced row echelon form, what we want to do is divide row 1 by, we want our pivots to be 1, so we're going to have to divide row 1 by 3. So there we go. So this is RREF. Okay, now what? So now let's write our general solution, but I'm going to write the general solution as a vector. So my vector is x1. We have a total of 3 variables, x1, x2, x3. X3 is free. So what we're going to do is write x1 in terms of x3. It's going to be 4/3 x3. x2 in terms of x3 is just 0. Notice that x3 there is, or excuse me, x2 is 0 x3s. So we just want 0. And then x3 is free, so it's itself. Okay, so now what we get here, we can pull out the x3. We're going to get negative 4 over 3, 0, and 1 if we pull out x3. And so now let's write the solution as a vector. A vector. Well, I guess we've already written the solution as a vector form there, but we'll let this vector, you could say that vector is u or something like that, or I could let x3 be 3. So if x3 equals 3, then that simplifies our vector there a little bit. We get negative 4, 0, 3, and then we can say t. So now we're just using parameter, use parameter for free variable. And this is our parametric vector solution. So now all solutions of this system above, up here, all solutions of that system can be represented as negative 4, 0, 3. So we don't want any x2s here in order to get a solution. So let's test it out. How about we plug in, let's plug in, how about we double, no, let's just keep it negative 4 and 3, so let's just try it in the first equation right here. So we'll do 3 times negative 4 plus 5 times 0 minus 4 times 3. So we're going to get, is it a minus 4 times 3? Uh-oh. I am getting a negative 12, not 0. Negative, negative 12. So let's see, did I make an error somewhere? Whoops, I picked up a minus sign. I'm glad I checked it. So this minus, you probably saw that in your notes and were barking at me as you were doing it. So there should be no minus there. So let's fix that. There we go. So it does equal 0 for the second equation. Let's just be sure and check so we checked the first. Let's check the second equation here in a different color. So we're going to have negative 3, 4 plus negative 2 times 0 plus 4 times 3 is going to give me, again, 0. Yeah, so this should satisfy each equation. Not only does it satisfy each equation, but if I scale this, if I let t be any value, like 10, that solution will still work in every one of these equations. So this is the vector parametric form of the solution. So every value that I pick here for t will end up giving a new solution. Yeah, so here they say describe the solution set of this homogeneous system. I put system in quotations there because a system usually has more than one equation. So this really doesn't have more than one equation, but we can still consider it a system, I suppose. So let's write the general solution. Well, let's write x1 in terms of the two free variables, x2 and x3. If you write this as an augmented matrix, it would look something like this. Right, and so x2 and x3, notice that they don't have pivot elements in those columns, so we're getting free variables from them. x1 is just a basic variable, so let's write x1 in terms of x2 and x3. So here we're going to have 5 x2s plus 7 x3s is x1. Let's use black there. And then these two variables are just free. So x2 and x3 are free. So now what we want to do is break this up into an x2 vector. So in the first component, I have 5 x2s. In the second, I have 1 x2. In the last component, I don't have any x2. Now, how many x3 do I have? Well, I have 7 x3 in the first component, 0 in the second, and 1 in the third there. So now we replace each one of these with parameters s and t. and then we have a parametric vector form of our system. So you choose any S and T you want, and then you're going to get a solution vector for this system. Now, it's completely independent of S and T that you choose, so we have a lot of solutions here. In fact, the spanning set of the solution here would be the span of these two vectors, which is going to be a plane. So it's all the solutions of this particular system lie on a plane, which, if we think back to multivariable calculus, this is, if you replace x1, x2, x3 with x, y, and z, we get a plane. So I've got a class coming in, so I'm going to go ahead and pause it there and continue in a minute. Okay, I'm back here at the end of the day. Let's continue. It says describe the solution of ax equal b, where the matrix A and B, the vector B, are given. Okay, sure. So let's go ahead and augment 2 and then row reduce. It looks like this is the same matrix as the previous example, and so we will augment like so. Now here we already know that. Whoops, that's not a vector. We already know that this is going to have an infinite number of solutions. Let's see, we did this matrix right here. So we noticed that the solution set is of the form 4, 0, 3. Now, is this vector B 4, 0, 3 right here? If we have a look at it, it's not of that form. So is this system going to be consistent? Is this the same matrix? Let's go back and look at this one. 3, 5, 4. Oh, no. They look exactly the same to me. I don't see any difference. Just comparing the matrix A here. So I'm wondering if because we've already seen this here, if we're not going to have a solution. But let's go ahead and augment and see what we get. Hopefully we can find it here. So let's go ahead and row reduce. Okay, it's positive 6. Okay, same row operations as before. So first row is going to remain unchanged. These two will be zeros. We want to add row 1 to row 2 to get 3, 0, and then we're going to get a 6 here. And let's see, and then we'll subtract 2 of row 1 from row 3 to get a negative 9 here, and a 0, and 2 7s, it's a negative 18 here. And then we're going to see that last row eliminated. So this is going to, we'll divide row 2 by 3. And then row 3 will eliminate by taking 3 times that and adding it to 3 times row 2 to add it to row 3. So this row is eliminated. Sure. And so far, the system here, we see it's consistent. So what was it that we were saying before? So this is for the homogeneous system, for the homogeneous solution. So remember, if we look back at our theorem here, the solution set is going to be P plus VH, where P is a solution of the homogeneous equation. So, or VH is a solution of the homogeneous equation. So it's off by a factor of the solution here. So we're finding that that we are going to have a solution. Let's go ahead and eliminate that 5 by subtracting the 5 of row 2. That's going to be a negative 3. And then we'll divide row 1 by 3. That's going to leave me with minus 4/3. I dropped, whoops, not 0 there. I dropped a row of zeros here, so let's put that back in. And this is a 2. All right, sure. So we have one free variable. They want us to describe the solution set, which is a little vague. They didn't give me a specific a specific way that they want the solution. So I'm going to give them a couple different solution descriptions here. So the first is the vector form of the solution. So we have x1, x2, x3. Now the free variable is x3. No pivot elements in the column. So x1 is really just 1 plus 4/3 x3. So 1 plus 4/3 x3. x2 is a constant 2. And then x3 is free. So now the solution set can be described as the vector 1, 2, 0 plus x3 times the vector 4/3, 0, 1. Like that. Now here is our vector. This is the homogeneous solution vector VH, and this is like our vector P from our theorem that above, remember? So if we go back here, so we have our solution vector P from this system, and then VH is the solution vector from the homogeneous system, which we did before in example 1. So here we can write this as x equal 1 to 0 plus t for 4, 0, 3. So I chose x3 to be 3 there. So now this is a cleaner form of the solution set. So now what if I let t be 0? So then the vector 1, 2, 0 should be a solution. So 1, 2, 0, if I take 1, 2, 0 and multiply, I should get the vector b, 7, negative 1, 4. Now, you have to weight each one of the columns to figure that out. We could just do the first element here. If I weight 3 by 1 and 5 by 2, that's going to be, that's not going to get me 7. So what am I going to get there? Something's not right. Am I missing a minus sign? Let me pause the video and see my work, double check. Once again, you were probably shouting at the computer here. I did miss a minus sign. It's always good to check. There's a minus right there after the 1 when I divided this row by 3. Somehow I dropped the minus. Whoops. Let's go back here. And we'll take away the red there. Okay, so very good. So how does that change my answer here? This is a -1, and this is a minus. There we go, and this is a minus. So let's see if that fixes this. So this is a minus. Then I'm going to get 10 minus 3, which is 7. Okay. It's always good to check your answer. Yeah, so I hope you see, that when you're taking a test, like, remember, I told you transcription errors are the biggest errors in linear algebra. You're going to make a transcription error. So then how are you going to catch it? That becomes the question. How do you catch your transcription error? I hope you saw, that literally took me like a couple seconds off of the video, so I wish I kind of would have done it on video, but I just paused the video, and I looked back through, and I realized, hey, there should have been a minus sign because when I weight 3 by 1 and 5 by 2, I'm not getting 7. So I was weighting my columns there to try to check my answer. And so that little tiny check caused me to come back here and look at where those numbers were coming from. So I looked at this 1 and the 2, and then where did that 1 and the 2 come from? So it came from those 1s and 2s. And where did that 1 come from? It came from over here, and then I realized I had missed my negative sign. So it was just a little bit of a backtrack, and the more you do that, the better you'll become at it, but it takes a little bit of time. So the other way that we could represent the solution here is that it's a line through this point. So this is a line through T-H-R-O-U through the point -1, 2, 0 in the direction 4, 0, 3. So that's another way that you could kind of geometrically describe what the solution set is. It's a little bit more concrete than in this abstract kind of vector solution. Okay, the next one says describe the solution to the following system in parametric form and provide a geometric description, as I did in the previous one. So let's go ahead and immediately convert this to an augmented coefficient matrix. So we have 1, 1, -3, 3, 4, -7. Make sure that you're not making transcription errors as you write these down. It's so easy. I can't tell you how many times just copying the coefficients from the equations to a matrix I've made mistakes. You just want to be careful. Okay, let's start down our row reduction. First row is going to remain unchanged. These will be zeros. I'm going to subtract 1 of the first row from the second row to get 1, and that's going to be a -3 and a 3. Here, adding 3 of the first row to the last row to get 2, and that's going to give me 15 and 9, so -6. And then this should be, let's see, 3 times 4 is 12, plus the 6 is 6. Okay, sure. Notice that the second row is going to eliminate the last row. So this last row will now be a row of zeros. If you subtract 2 of the first row from the second row, or the third row, you'll get zeros. And now this, I have to subtract 3 of the second row from the first to get 4 there. Is that going to be a 4? So you add 9 to the 5 to get 4, -5 to get 4, and then we're going to subtract 9 from the 4 to get -5. They swap places there. Whoops, not a 0. That's going to be a -3 and a 3. Okay, very good. So this is RREF. That takes a little bit of time and decision to make sure that you get there. I did it very quickly, so I could have made a mistake. Hopefully I didn't. We can check it at the end. But let's go ahead and write our parametric vector form of the solution. So x is going to be x1, x2, x3. x3 is the free variable here, so we want to write x1 in terms of it. So it's going to be -5 minus 4x3. And then we have 3 plus 3x3, and then x3 is the free variable, so you just have 0x3, 0 plus x3. Okay, so this is really, let's write this as 2 vectors, the constant vector, plus x3 times -4, 3, 1. Are the coefficients of x3. So now I can write this, let's write it in a different color. We can say x this is the parametric vector form, plus t. We'll just let x3 be t, and 1. Sure, there we go. So parametric vector form of the solution. Okay, and what did they ask? Geometric description? Same interpretation as the previous problem. This is a point right here, and this is the extrusion in a direction of -4, 3, 1. So this is a line. So we have a line. Let's write line through -5, 3, 0 in the direction of you can write it as a column. I'm just going to use our multi-notation here. Probably better to use a column so that we keep the notation as similar as possible. So we'll just replace it there. Yeah. All right. So that's the idea there. Finding a solution and then writing it in parametric vector form, and then going further and giving a geometric description. Now, what if I had 2 free variables? So what if I had a t and an s? Well, then that would generate, of course, a plane in 3 space. What if I had no free variables? Well, then that would just be a point in space. So you have point, line, plane, and then, of course, it goes dimensionally higher out of the dimensions that we physically can represent in 3 space. So you could have all of 3 space. I guess that would be a really silly system. So this is the idea here behind parametric vector form. So next class, I would like to try to give you guys a quiz. So let me maybe write that down. So we'll say quiz on Friday. That's 2/6. 2/7. And what? What's on it? So 1.1, of course, through, I think I determined 1.4. So not what we just did. So 1.1 was introduction to row operations and row equivalents. And then 1.2, I think we got to, so this is 1.1, 1.2, we got to row echelon form and reduced row echelon form. Did we talk about anything else in 1.2? I think that was it. Let's go look real quick. Elimination, pivots, so that we had learned the vocabulary of pivots at that point, of course. And we talked about general solutions, so that's something else. So we'll say in general solution. And then 1.3, we learned, let's see, 2 classes ago. I did a video on that one, didn't I? Where's 1.3? Vectors. Yeah, so we learned all the properties of vectors. I think I did a video on that one. And vector equations, and learning how to represent the weights of vectors. So that was linear combinations. So we started linear combinations. And then we did matrix equations last class together. So let's go ahead and put that on the list there. Okay, so then we have, this was vectors. And then we did linear combinations. And spanning sets. I'll just say span of a vector, span of vector set. And we determined how to tell whether or not a vector is in the span of a set. And then 1.4 matrix equations. What was nice about matrix equations is we started representing systems as matrices and their solutions as vectors, which was kind of a novel idea. We introduced AX equal B like that. We hadn't talked about homogeneous solutions. That was today in these notes. So yeah, you want to look over those. We did some row reduction, and I think we introduced we didn't introduce parametric vector form yet. That was this class. We learned how to do the product of matrices in a vector, and we learned a theorem that distribution of a matrix on the left of a vector. Here we found a solution, determined whether or not it was consistent, which means it's in the span of the columns. Yeah, so representing vector equations, that wasn't too complicated. So this is the content for the quiz. So this is quiz 1. Yeah, look over the homework. I will be in class on Friday, so I should be able to talk about any homework questions you have over those sections before the quiz, so I should be good. But yeah, I think that's it. Well, thanks for watching if you made it this far, and I will see you guys on Friday.